All right, today we're talking about lowest common ancestor and binary lifting. Yay. All right, so what is the lowest common ancestor problem? You're given a rooted tree as shown here, and you're given two nodes, and you're trying to find the lowest common ancestor of those nodes in this rooted tree. And what does that mean? What does an ancestor mean? We all know about the, what's it called, parent-child analogy in the terminology of trees. So that's the parent of this is child of that. And of course, it naturally extends to like the whole family vocabulary. Like they are like, I don't know, third cousins or something, right? Then that's an uncle or an aunt. And so, yeah, ancestors means you're like a parent of a parent or something. Like your parent is an ancestor, your grandparent is an ancestor, your great grandparent is an ancestor. So lowest common ancestor. So we now know what ancestor means. Common is a canonical word, so we know what that means. And what does lowest mean? It just means like lowest on the tree, graphically shown. So okay, so that's a common ancestor of these two nodes highlighted. And that's also a common ancestor of these two nodes highlighted, but this one is the lowest one. Or if you want to formalize it, it's just the one with the greatest left. So here, if we're trying to find the lowest common ancestor of this node and that node, that's not a common ancestor, not a common ancestor, that's a common ancestor, and that's the only one. So it's the lowest common ancestor. Yep, as shown here. Those are the lowest common ancestors. Okay, and now if we formalize it, given a rooted tree T and nodes U and V, I want to find the node W such that W is an ancestor of U, ancestor of V, and W has maximum possible depth, while satisfying the previous two conditions. And what can we use the lowest common ancestor to do? We can very quickly compute the distance of two nodes on a tree, like an O of 1. So distance between U and V is the distance from U to the LCA of U of V, E and V, and plus the distance of between the LCA of U and V to V. So if you expand it, it's this. All right, and to solve this problem efficiently, we can actually phrase the problem another way. If you look at the path from the root to each of the two nodes given, you see that the lowest common ancestor is last node that's in the common prefix. So if you actually number the nodes and write the paths out, they have a longest common prefix, and those are all the common ancestors. And the last one of that common prefix would be the lowest one. So using that way of phrasing the problem, we can find an algorithm to do this efficiently using binary lifting. So the binary lifting goes as follows. First, for each node of U, we compute, I don't know how to say this, ancestor. I think when I learned it, they called it ancilla. I don't know what that means, but I'm just gonna say anc of U and K, which denotes the 2 to the kth ancestor of U for k from 0 to log n. Because the largest distance you can have in a tree of size n is 2 to the log n. And then we suppose without loss of generality that U is higher up in the tree than V. So we just find an ancestor of V prime of V such that they have the same depth. So they're on the same level by binary lifting, which I'll explain later. And then if U is equal to V prime, so if this node that's on the same level is the same node, then that is the LCA. So if you think about a tree that's just a path, and U is the root, and V is like the leaf, then if you lift V up to the same depth as U, then that's the same node, which is U. That is the common ancestor, and that's the lowest common ancestor. And if that's not the case, then we want to find a node W prime such that W prime is an ancestor of U, and the ancestor of V prime that's on the same depth level is not equal to W prime. And if you think about that, that's just like the fork right below the lowest common ancestor. And the parent of W prime would be the LCA. And I'll show you graphically what that means. So Where's my graphic? Okay, the graphic is here, I guess. Yeah, so given these two nodes, and never mind, this graphic sucks. Let's just go back. Let's just go through the algorithm. Yeah. Okay. So for each node u, we want to compute enc of u and k. How do we do that efficiently? If you think about it, a brute force computation would take O of n time for each node. Because you start from the node and you keep going up. Like you go up to the 2 to the 0th parent, and then you go to the 2 to the first ancestor, and then you go to the 2 to the second ancestor. So you just have to go up until you hit the root, which is O of n. So it would take a total of O of n squared time. But if we observe that the 2 to the kth ancestor is of u is the 2 to the k minus first. Oh, k minus first. Oh, I spelled it wrong. K minus first ancestor of the 2 to the k minus first ancestor of u. Does that make sense? Then we can just compute enc of u comma k plus 1 for all u if we have enc of u comma k for all. And we can do that in O of n. And since k goes from 0 to log n, it's a total of n log n complexity to pre-compute. And here's the pseudocode for the enc computation. The base case is for the root, the parent of the root is just the root. It makes it easier. And for every other node, the parent of, or enc u comma 0 is just the parent of u. And then from there, we can do the inductive step. And now let's see how we binary lift v to v prime such that it has the same depth. So what does this mean? How do we find this v prime ancestor of v such that the depth u is equal to the depth of v prime? First of all, does everyone know why we are like what this means at all? Finding a v prime that has the same depth as u? Not hearing anything, so I'm gonna take that as a no. So like in this case, if we lift them to the same depth level, they're already on the same depth level and they are not equal. So that's the second case in our algorithm. So so we would skip 3 and go to 4. But in the other case, so here's u, which is higher, and here's v, which is lower. If I lift v up to the same depth level as u, I see that, oh, they're the same node now. So that means that's the LCA. But yeah, that's what I mean by lifting them to the same depth levels. So if v prime was here, lift it to here. But that would be O of n if we didn't know much any better. So we need to use binary lifting to find this v prime in O of log n. And how do we do that? We lift the node in decreasing step sizes. So initially we set v prime to v. So we start at the node, and starting from k equals log n down to k equals 0, we lift the node by 2 to the k only if it stays at or below the depth of u. So if you think about it, it's always going to work because it's basically, so like there is a difference in the depth, right? That can be represented by a binary number, say like, I don't know, 5. And if you do the step, so suppose your log n goes up to 4, so that's like 2 to 4, which is 16. You try from k equals 4 to 0, we see that, oh, can I lift it by 2 to 4 equals 16? No, that's too high. Can I lift it by 8? No, that's too high. Can I lift it by 4? Yes. But now it's just a difference of 1, and then I try lift it by 2? No. Can I lift it by 1? Yes. That's basically just taking the bits off the binary representation of the distance. All right, and if you think about it, that's really similar to a binary search because you basically have like a 1D array where the first half is false, the second half is true. And you're lifting it back to the front as far as possible until it's like false. And okay, now for the next step, how do we find this node W prime? That is the highest node that's an ancestor of U, such that the node on the same level as an ancestor of V is not the same as this node. Does that make sense though? Those are the two nodes right below the LCA. Anyways, we do the same thing. We lift both u and v prime at the same time this time though. And we only lift them by some amount, some 2 to the k, if they like stay different. So if you think about it, if we lift them too high, they're going to be on that longest common prefix, and they'll be equal. So we want to find the end of that. We keep them unequal, and in this case, we're trying to find the LCA of these two nodes, and so our log n goes up to 2, yes. So we try to lift them. 2 to 2 equals 4, which both goes to this one, but it's equal, so we don't want it. Now we try 2 to the 1, 2 to 1, so we lift them by 2, so they go here, and they're still different, so that's good. Then we try 2 to the 0, which is still moved by 1, so they're still different, so that's good. Then we're done. And then the parent of any of these will be LCA. And actually, there is a more advanced way to do LCA in O of 1. While our binary lifting technique only gets us to O of log n with n log n precomputation, but it's possible to do an O of 1 with the same amount of n log n computation using this O of 1 range minimum query trick, which you can check it out yourself. And there are more applications to binary lifting, and it doesn't only just do LCAs. You can like repeated squaring in fast exponentiation is kind of, I would like to think of it as binary lifting. And sparse tables, if you know what they are like basically an alternative to big trees, except it only works for static arrays, so there's no updates, but it can do O of 1 queries, O of 1 range minimum queries, and with O of n log n precomputation. So that also uses binary lifting. I mean, if you think about it, O of n log n precomputation, O of 1 queries, that just sounds like what I just said. Does it? Wait, it doesn't. It doesn't really. But it's n log n precomputation, and that sounds like binary lifting. And then there's also this blog on binary lifting in Fenwick tree, which some people call binary searching on Fenwick tree. I don't know. You can read it and figure it out for yourself. And then there's more further readings for that here. And then I would like to advertise Codesprint LA 2023. It is the most exciting event that you'll ever see in your life, actually. And it's Sunday, May 21st, so that's in like 2 weeks. And it's that time, and you can register right now at this time, which is closing next week. Then there's the contest, which features a lot of our codes, actually solely features Codesprint LA 2022 problems, other than the ones that are related to LCA. So have fun.